Hello and welcome to my dissertation defense talk. Today I am going to present two disjoint discussions. The first of them is regarding finding holes in potential energy surfaces. We'll start out by addressing what potential energy surfaces are and what holes are doing in them. To get started, I have a representative two-dimensional surface on the right side with this additional colored axis representing a function on this surface. In general, the word holes refers to a region of the surface where the function slides downwards towards negative infinity. In this case, we are talking about this blue region on the right side. Next, we'll discuss why it is important to find these holes. And finally, how we find these holes. Specifically, we'll discuss our algorithm Crystal, which we developed with this hole finding purpose in mind. Finally, we'll talk about how our algorithm can be applied towards finding holes in potential energy surfaces. Our second discussion is titled An Unorthodox Study of Bidirectional Light Waves. We begin this section with a question. If we have a standing wave, here in this image, the black curve is the standing wave and the red curves are the plane waves which create the standing wave. And this is a moving observer. Then the question is, what does this standing wave look like to this boosted observer? The answer actually depends on whether we are thinking of a Galilean boost or a Lorentz boost. Galilean boost is very intuitive. All that the moving observer will see is the same standing wave, except that it's moving backwards for him. On the other hand, if we do a Lorentz boost of the standing wave, we see something more interesting. We see these packet-like shapes. What are these and where are they coming from? Well, this effect can be understood as a result of how simultaneity works in relativity. For standing waves, all the peaks rise and then fall at the same time throughout space. However, in relativity, things which are simultaneous in one frame of reference will not be simultaneous in a boosted frame of reference. As a result, there is a phase difference between the rise of one peak and the rise of the next peak. These phase differences add up and create an illusion of a moving wave here. Now here's something interesting, and this has probably not been reported, at least as far as I know, anywhere in literature so far. If you write down the energy of the standing wave as h bar omega and then let m equals E by c square, then it turns out this large wavelength is equal to the de Broglie wavelength. Now this is interesting. What are de Broglie waves doing in electrodynamics? We do not have any quantum mechanical differential equation here. We just have standing waves of light and a moving frame of reference. So what do we make of these de Broglie waves? We'll examine this in details in the second discussion, and we'll see how this ends up leading to more fundamental questions like what is mass in the first place, and things like perhaps the quantum mechanical mass is not the same thing as inertial mass in classical dynamics. Let us get to the first discussion now. We are going to find holes in potential energy surfaces. The idea of potential energy surface comes from the Born-Oppenheimer approximation. According to this, nuclei are much heavier than electrons. Because of that, electrons move much faster than the nuclei. As a result, the electrons respond nearly instantaneously to any change in nuclear movements. This means that the electronic wave function can be approximately known using nuclear coordinates alone. The potential energy surface, then, is the expected electronic energy as a function of nuclear coordinates. This is uniquely defined because the electronic wave function only depends on these nuclear coordinates in the limit of the Born-Oppenheimer approximation. Now, why is it important to find these holes? It is important because holes can cause theoretical dissociations in molecules much before the experimental energy that it requires. This poses an artificial upper limit of energy above which quantum calculations can be performed. If this was a two-dimensional potential energy surface and the red contour was the energy of the molecule, then it would quickly go into the hole and dissociate. Holes are a result of bad fitting. Now, to be fair to PES developers, when we say bad fitting, we do not mean that the PES developers are bad or they don't know what they're doing. Bad fitting happens because fitting is very difficult in higher dimensions. If I want to fit a surface like this using polynomial terms up to the fourth order, it is computationally easy. We have expansion terms like x square, y, and so on. There are a total of 12 such terms. It is easy to fit and find 12 coefficients using the least square method. Now, if there are over 30 dimensions, the number of expansion terms becomes ridiculously large. It goes over 100,000. Computers cannot perform such fits. So you have to select which polynomial terms you want to keep and which ones you can discard. You also need to decide which nuclear geometries are important for fitting. There is a lot that can go wrong there. So what we are doing with this algorithm is we are trying to make the job of PES developers slightly easier. We are providing them with a method to find these holes so that they know which nuclear geometries need to be fit and what expansion terms need to be added to remove the holes. Now I will explain our algorithm. Crystal algorithm is designed to find all connected PES lattices which lie inside a desired contour. The energy of the contour is denoted by V cut and the number of lattice points inside the contour is denoted by n. So we started with one lattice point inside the red contour. This lattice point then looked at its adjacent lattices and added them to a list. Then its adjacent lattices looked for more lattices around themselves and added them into the same list. Now formally, here is the bigger picture of how crystal algorithm works. The red lattices find the set of black lattices around themselves. One black lattice over here got rejected because it was lying outside the red contour. The remaining black lattices found the set of brown lattices around themselves. Again, those brown lattices which were outside the contour got rejected and the rest were accepted. Finally, the brown lattices found the green lattices, out of which only two were inside the contour. So, at any moment of time, the searcher lattices are the lattices that are currently searching for new lattices. The new lattices form what we call as the simplicial shell. Of the simplicial shell, those lattices which are inside the contour of interest are accepted while the rest are rejected. The accepted lattices then become the new searcher lattices and look for more points around themselves. Now there are two ways in which a lattice can get rejected here. One is if it lies outside this contour. The other is if it was already found by a previous searcher lattice before another searcher lattice found it again. In other words, we don't want to accept duplicate lattices. So, the crystal algorithm uses a sorting process which can check for duplicate points and remove them. Crystal utilizes a novel merge sort technique. On the right side, I have a graphical representation of a merge sort technique. This is called a binary tree. There are two things that compose a binary tree. One is these vectors themselves and the other is these arrows. The arrows are created using a predefined comparison scheme between the vectors, which decides whether an element will go to the left or to the right of another element. Now, in our binary tree implementation, vectors were first mapped to natural numbers. This made it possible to implement arrows by using two simple arrays, left and right. For example, if you want to say that the fourth vector is to the left, the sixth vector is to the left of the fourth vector, this is done by saying left of 4 equal to 6. Now, there are other sorting techniques which are used by different libraries, such as the hash tables, and the textbook approach is to use linked lists, which are represented here on the top right side. We have not compared our method with all these different techniques, but our method does work much faster than the linked list approach for the purpose at hand, which is to simply find and store lattices without needing to actively retain any other kind of information. Now, there will always be some situation in which each different sorting method will specialize in doing something faster than the other methods, but for our purpose, we decided that our approach is optimal. Now let us consider a higher V-cut contour that spills into the hole. We want to find the whole saddle point that turns downwards into the hole. The most obvious way to find it is by observing that the potential energy increases as we go outwards inside the region of interest, but once the whole saddle point is reached, it starts falling as we keep going further. So, if the potential at the searcher lattices, denoted by U, is higher than the potential at the simplicial points that it explores, denoted by V, then it means that we are probably inside the whole region. We can stop the code there and check if there is really a hole there. Unfortunately though, this method results in too many false positive holes in anharmonic surfaces, especially in higher dimensions. However, this method is effective for salvaging bad PASs by avoiding holes. Basically, the U less than V rule will avoid holes for sure, but it might also avoid certain other points or regions which are not holes. So, it would be hard to say definitively which points the hole are, because it would sometimes just output too many points which are prospectively holes. So if you need to perform dynamics calculations and the only PES available is riddled with holes, then you can use this method to avoid holes and perform calculations that are alright. However, to find holes reliably, we need a different approach. Before we can talk about that approach, I need to explain a concept which will be very useful for it. Notice how, in the left figure, the algorithm grows out in a perfect simplex or perfect diamond shapes during its early stages. This happens because the algorithm cannot see the inner contours. It can only see the outermost contours when it checks whether the potential is less than V-cut or not. However, on the right side, we see a process that we call as layering. This is done by filling in the inner contours before going further to the next contour. Here, simplicial shells will maintain the shape of the inner contours as they expand outwards. Now we are ready to find holes. Hole finding is done in two steps. First, we find a narrow range of energy between two values V1 and V2 such that the lattices spill into the hole for the V2 contour, but they do not spill into the hole. They remain inside in our region of interest for the V1 contour. Now, it might appear that we can take the red contour as V1 because it's like definitely inside, and the outermost brown contour is V2. But no, for certain reasons which we will see very shortly, V1 and V2 should be as close as we can get. probably more like the green and the blue contours in this figure. Now please bear with me for a moment here because I have to digress for a quick short note. Although the blue contour is unbounded here, it does not spill into the hole. Why? Notice that because the lattices are discrete, it turns out there is no continuous path for the code to get into the hole through these blue contours. The crystal code does not travel diagonally, and it cannot go up or right from this point over here because both those points lie outside the blue contour. This is what we call the discretization problem or the chunkiness problem. We have ways to deal with it, but we won't be discussing that today. For now, we'll carry on by choosing the blue contour as V1 and the brown contour, the outermost brown contour, as V2. Now finally, coming back to our topic, we will perform crystal with V cut equals V2 but with a layer at V1. The layer was what we had discussed in our previous slide as fitting the contour first before going outside. So first, our code will find all these blue points before going any further. After that, it searches for the next simplicial shell, which we denote by the brown lattices. Notice how if blue and brown contours are very close to each other, I mean if V1 and V2 are very close to each other, then the next simplicial shell will contain only these two whole lattices. We can stop the code and report these two lattices. However, if V1 and V2 are not close enough, then other than these two lattices, the code will, this simplicial shell will also contain more points which will lie elsewhere outside the blue contour. We don't want that to happen. So that's the reason why we narrow the difference between V1 and V2 before doing this part. Now the whole lattice is not exactly the same thing as the whole saddle point because lattices are discrete, whereas the true whole saddle point lies in the continuous space. So the crystal algorithm includes a trivial gradient minimization procedure to help find the exact whole saddle point. This module can be used after finding the lattice whole point. In a gradient minimization procedure, if the starting point is close enough to the whole saddle point, then the exact location of the whole saddle point is obtained as an output. In this image to the right, the black lines represent the points of zero gradient, and the red lines represent the regions where the gradient is locally the maximum. If we apply a gradient minimization procedure starting slightly to the right of this red region, it will take us up to this black line. Similarly, if we start to the left of this region, it will take us down to this black line. In general, the gradient minimization procedure will take you to the nearest minima or maxima or saddle point or inflection point, or sometimes even to some sorts of non-zero gradient points. But long story short, as long as we start close enough to the whole saddle point, it should lead us to the exact whole saddle point. Now, how do we start close enough to the whole saddle point? Well, the lattice whole point that Crystal found in the previous slide is generally close enough for it. Now, as we discussed earlier, fitting a PES can be hard. So PES developers might want to know multiple holes so that they can patch them together rather than patching one hole at a time. We have a plugging technique for doing that. The lattice hole points can be blacklisted manually, plugging one hole at a time. point plugs and cubic plugs have been implemented. Basically, if you blacklist this point, crystal cannot accept it, so it won't go into the hole for the brown contour. However, it can still go into this hole again if you increase the energy enough and reach the yellow contour. Then crystal can snake around this point from the top or the bottom and reach the hole. Now, in such a case, many more points here might need to be plugged before crystal can find the next hole, which is over here. For higher dimensional PESs, this can mean plugging a huge number of points around this region. So we make this task easier by collectively plugging all points that lie in this yellow cube around this black point. This is called a cubic plug, and that just makes it easier to find many holes one after another. Now finally, it's time for some results. The first column here is the molecules that we inspected. The second column is the degrees of freedom or the dimensionality of the PESs of these molecules. The third column is the energies of the lowest lying holes of these molecules. The fourth column is the number of significantly displaced degrees of freedom, which means the dimensions which essentially have non-zero values at the hole configurations. What is the most noteworthy here is how low the holes are for these higher dimensional molecules. Such low energy holes can definitely have significant impacts in dynamics calculations. We are the first group to report holes for molecular PESs. However, that does not mean that holes have not been suspected earlier. In one paper, Carrington's research group suspected a low energy hole in this uracil PES because they got some garbage results from using it. But they did not mention the energy or the configuration of that hole. In that same paper though, they also performed calculations using this naphthalene PES. We see here that the naphthalene hole is in fact much lower than the uracil hole. The highest harmonic frequencies for naphthalene and uracil are actually comparable. So in all likelihood, their naphthalene results would also have been affected by this hole. With regard to holes, Carrington's group in that paper only went so far as to say that the uracil PES seems to have a hole below its 0 point energy. Now that 0 point energy of uracil PES is over 18,000 centimeter inverse. So yes, they were right in that regard. This hole is indeed much less than that value. But that also holds true for naphthalene, whose 0 point energy is in fact over 30,000 centimeter inverse. As for this benzene PES, it has also been in the market for decades, and it might have resulted in many bad calculations too. Now here are some performance benchmarks for the crystal algorithm. It finds roughly 2 million PES lattice points per hour for naphthalene, which is a 48 dimensional PES and has 4173 polynomial expansion terms in its potential energy surface. The computational time scales linearly with increase of degrees of freedom for a constant n, and the computation time scales as n log n for constant degrees of freedom. In conclusion, crystal successfully found holes in molecular potential energy surfaces like benzene, uracil and naphthalene at surprisingly low energies. The benzene and naphthalene holes were so far unsuspected and might have affected a lot of molecular calculations. Computational chemists should use the crystal algorithm to inspect PESs for holes before performing calculations using them. PES developers should also use crystal to inspect PESs and patch their holes before publishing them. Crystal may have applications beyond finding PES holes. We have used this in one of our earlier projects, and we have some speculations about how and where it can be used. All this has been elaborated in the dissertation. Let us move on to the second project now. Classical trajectories obey Newton's law, which states that an object will remain at rest or in uniform motion in a straight line unless acted upon by an external force. Quantum trajectories, specifically Bohemian-like trajectories, which are the most popular quantum trajectories, they can interact with each other in absence of an external force. Strictly speaking, there is a caveat here. This statement is not completely true. In free space, particle wave functions are plane waves. They do not interfere unless a part of the wave function is reflected or slowed down by an external potential. In some sense, they have interacted with the potential. But what I mean here is that the quantum trajectories interact with each other. This is not so surprising when there are many particles, but it is well known that interference patterns are also obtained if one photon is sent at a time in a double-slit experiment. In that sense, the photon is interfering with itself. For the rest of this discussion, please keep only a single photon picture in mind. Unless we mention otherwise, we are only talking about single photon waves. Now these images are taken from these sources mentioned here. However, I can attest that this image here is accurate because I have seen similar results for myself. We were performing a double slit experiment in high school and there was some dust in the room. So what I saw was close enough to this. On the right side here, we have Bohemian trajectories corresponding to this image. One feature of the Bohemian trajectories is that they never intersect each other. It can be shown that the direct result of this non-intersection rule is that standing waves correspond to particles at rest. That makes standing waves the most non-intuitive Bohemian trajectories. If you apply them to standing waves of light, for example, then its photon is at rest. Now, if photons travel slower than the classical speed of light, they are, relativistically speaking, massive because they follow matter-like curves instead of light-like curves. For standing waves, it can be shown that the mass of these photons, which are at rest, will be given by this quantity here, which turns out to be E by c square. So what is the correct quantum rest mass of a standing wave photon? Is it 0 as classical relativity expects, or is it E by c square as Bohemian-like relativity expects? Equivalently, what we are trying to ask here is, does a standing wave photon have the properties of a massive quantum particle? We saw very early at the introduction that, well, they do have de Broglie-like waves. So this raises a question of how particle-like these standing wave photons really are. By the way, here gamma is the Lorentz factor. At the top right here, we have standing waves, and at the bottom right, we have the Lorentz boosted standing waves, or the bidirectional waves. We can almost go from here to here through two steps. Step 1, boost the standing wave as in a Galilean boost of velocity v0. So now we have just the same standing waves but translating forward. Step 2. Multiply this wave with this red wave, the red de Broglie wave, moving at the velocity c square by v0. This gives us the bidirectional waves. Note that the red wave velocity c square by v0 is always faster than the speed of light. For this reason, we call the red wave the superluminal wave and this black wave as the subluminal wave. Incidentally, the velocity c square by v0 is exactly the Klein-Gordon phase velocity. There is a reason for this similarity which we shall shortly see. Anyways, bidirectional waves can be shown to be a product of these subluminal and superluminal waves. Let us now look at the individual plane waves in the top right graph, these red waves. Both of them will transform as per the relativistic Doppler effect when the observer is boosted. So we can call the right moving wave as the plus wave and the left moving wave as the minus wave. So then this bidirectional wave can be written in terms of the plus and minus waves. Let us see what happens in the limit of standing waves. For standing waves, k plus equals k minus and omega plus equals omega minus. Then the subluminal frequency and the superluminal wave vector become 0. This quantity and this quantity are 0. Thus the bidirectional wave takes the familiar form of sine kx cos omega t for standing waves. Now the subluminal wavelength is found to be equal to the Compton wavelength. This is interesting and we'll talk about this later again. Earlier we had calculated the mass of standing wave photons. Now mass should be an invariant quantity, which means that the bidirectional waves should have the same rest mass as the standing waves. We checked it and it is indeed true. All the formulae of relativity such as constant rest mass and the relativistic inertial mass carry over correctly. There is an alternate interesting way to look at bidirectional waves. Let us make things look a little fancier here by writing the same bidirectional waves in a spherical form. Let us use cos kr instead of cos kx, where r is the radial distance. In the boosted frame of reference, cos omega t transforms like this and cos kr transforms like this. Interestingly, this term here is found to be exactly the same as the one-dimensional superluminal de Broglie wave. There is no y or z dependence here and the wavelength of this and the speed is exactly the same as before. As for the right term, I have plotted it over here. It simply looks like the length contracted version of the non-boosted frame of reference. It is very clear here that cos kr is affected by the length contraction, while the left term, the so-called time dilation, is what results in these de Broglie waves. In general, phi sub can be thought of as the internal structure of these standing waves, which does not change over time, while phi superluminal consists of the relatively independent de Broglie waves running over the whole of the structure. Often people have attempted to relate Klein-Gordon amplitudes to probability densities. The Klein-Gordon solutions can have negative probabilities, which are usually interpreted as anti-particles or as opposite charges. Our approach shows us that perhaps the Klein-Gordon waves cannot give the exact probability densities. We need to account for subluminal oscillations. It is no surprise then that the Dirac's equation solutions contain the Zitterbewegung oscillations which happen at the Compton wavelength. As mentioned earlier, this Compton wavelength is exactly the same as the subluminal wavelength. Now this is perhaps the most important question. How consistent is bidirectional wave dispersion with quantum mechanics dispersion? The dispersion of bidirectional waves is of course wave-like. However, the dispersion of the superluminal component alone is found to be Klein-Gordon-like. Why is this important? This is important because if you have wave-like dispersion and if you try to create wave packets out of waves which follow this dispersion, they will simply split and each piece will travel at the speed of light in opposite directions. This dispersion cannot give you particle-like behavior. In particle physics, for example, if you want to have interactions which travel at the speed of particles slower than the speed of light, you cannot get that using this dispersion. But you will get that if you have the Klein-Gordon dispersion. Now, the superluminal waves have this Klein-Gordon dispersion, and they spread out how spin-free particles are supposed to spread out. But together with the subluminal wave, the dispersion becomes wave-like. So the question is, can we somehow justify the separability of subluminal and superluminal contribution to the dispersion? It turns out that there is a way to separate the subluminal and superluminal dispersion, but it involves boosting perpendicular to the direction of the wave vector. Here the standing wave is in this direction and we are boosting perpendicular to it. Then we see superluminal wavelength in this direction while the subluminal wave remains in the direction of the wave. So yes, we will have some real particle-like dispersion in this direction only. So here for this wave, perhaps if we are in a little box over here and we boost in this direction, then yes, perhaps, but it's very limited in some sense. We want to have symmetry with respect to boost in any dimension. It should not be like if you boost in this dimension, it's like a particle, it's a particle-like behavior, and if you boost in the perpendicular dimension, it's a wave-like behavior. The only way to keep this symmetry intact and get this separation is if the standing wave lives in some fourth spatial dimension that we cannot see. Then in whichever direction you boost, you can see Klein-Gordon waves. But this is a very artificial way of doing it, and perhaps no one is going to like it. Although there are theories where people go into more than 3 dimensions. Now, there's yet another way to do it, and this way is also artificial, but it's better in some sense. It can be done by introducing second order like 2 photon wave like interactions as corrections to the electromagnetic wave equation. Photon-photon collisions are an inspiration for this approach. If a nonlinear electromagnetic wave equation achieves the correct photon scattering, it may also be expected to show bound solutions which may be considered as the equivalent of momentary electron-positron pair predictions. This possibility is enticing, but it will need a lot of work. Now coming back to this image, if we shoot a laser through a double slit, this is what we see. A laser shoots around 10 to power 15 photons every second. If we increase that number by a lot, we should eventually start seeing a change in this pattern due to photon-photon collisions and other effects. The idea is, if we have a non-linear electromagnetic equation that can correctly predict those changes in this pattern, then that same equation can perhaps have particle-like solutions too. In conclusion, bidirectional waves may offer an electromagnetic perspective towards understanding quantum phenomena without needing higher dimensional string theory-like approaches. I have string theory like in quotes because I am not an expert in string theory and my understanding of this theory is very rudimentary. However, obtaining slower than light particle physics interactions still requires the separability of the superluminal and subluminal dispersion, which we have not really achieved. As of now, we are not aware of any work that has been done on these lines. I hope to continue this research in future.